Section 2.5 Energy Accounting. Energy balance for closed system. So energy balance for a closed system is also known as the first law of thermodynamics. So this is a fundamental law of nature. It states energy cannot be created or destroyed. So we will be using this law frequently in solving thermodynamic problems. So change in the amount of energy contained within a system during some time interval equals net amount of energy transferred in across the system boundary by heat transfer during the time interval. So one of the modes of heat transfer, conduction, convection, or radiation, minus net amount of energy transferred out across the system boundary by work during the time interval. So energy balance can be expressed using symbols E2 minus E1. So energy at state 2 minus energy state 1 equals Q. Q, net amount of energy transferred by heat. So we can also write Q12 minus W, net amount of energy transferred by work. Or we can also write W12. The energy change in the system can be also written as kinetic energy change, potential energy change, and internal energy change. Internal energy is the sum of all microscopic forms of energy related to individual molecules and atoms in the system. There may be other forms of energy in the system. It may include surface energy plus surface energy, magnetic energy, electrostatic energy, etc. Typically, they are small enough to be ignored. So we usually consider kinetic energy change, potential energy change, and internal energy change within a system. The minus sign here before W is added since the work from the system to the surrounding is taken as positive. This is the sign convention we use for work. It's the opposite of Q. The word net indicates the amount of energy transferred in, subtracted by the amount of energy transferred from across the system boundaries. So here Q is actually mean Q in minus Q out. It's same for work. W equals W in minus W out. The first law of thermodynamics is also expressed as time rate. Time rate of energy change equals Q dot minus W dot. The dot over a symbol indicates time rate. And the unit of time rate of energy is joule per second or kilojoule per second. This is an example in our textbook. 4/10 kilogram of a certain gas is contained within a piston cylinder assembly. The gas undergoes a process for which the pressure-volume relationship is P, pressure times volume to the 1.5 is constant. This is a polytropic process. Initial pressure is 3 bar. Initial volume is 0.1 cubic meter. Final volume is 0.2 cubic meter. So let's say state 1, this initial state state 1, 3 bar, so pressure 3 bar, volume 0.1 cubic meter. State 2, pressure is unknown, volume is 0.2 cubic meter. Since PV, P1 V1 to the 1.5 is constant, P2 V2 1.5 they should be equal. So we can solve it for P2, which is only unknown here. P2, P1, V1, V2, 1.5. So P2 can be calculated. And also the specific internal energy of the gas in the process is U2 minus U1 is negative 55 kilojoule per kilogram. So internal energy denoted by uppercase U, internal energy U, uppercase U, is an extensive property. So it depends on the amount of mass. So you can be expressed as mass times lowercase u. So it's a specific energy, specific internal energy. So specific internal energy has a unit of kilojoule per kilogram. Kilojoule per kilogram. And there are no significant changes in kinetic or potential energy. Just stationary system. Determine the net heat transfer for the process in kilojoule. So what is known is we have a piston cylinder system and gas is within the system. It undergoes an expansion process. And specific internal energy is specified. And we need to determine the net heat transfer for the process. So process can be drawn on PV diagram. So pressure decreases, volume increases. It's an expansion process. Here are the assumptions. The gas is a closed system. The process is described by polytropic process. Pressure times volume to the 1.5 is constant. There is no change in the kinetic or potential energy of the system. So we are going to apply the energy balance. So kinetic energy change, potential energy change, and internal energy change equals heat transfer minus work transfer. So assumption is there is no kinetic energy change, potential energy change. It's a stationary system. So internal energy change equals the heat transfer, net heat transfer minus net work transfer. Internal energy change can be expressed m, mass times specific internal energy change. Q, heat transfer to or from the system. It can be also expressed Q1, 2 between the state 1 and 2. W can be also expressed W1 and 1, 2. So mass Q, solve it for Q, mass times internal energy change plus work. So mass is given 0.4 kilogram. Specific internal energy change is negative 55 kilojoule per kilogram. Work is 17.6 kilojoule. W12 was already calculated in example 2.1. So the positive work indicates the work is done by the system, which is an expansion process. So Q is calculated to be negative 4.4 kilojoule. So the minus sign for Q means the net amount of heat is transferred from the system to its surrounding. So Q, heat is transferred from the system to its surrounding. Also, work is done by the system. Example 2.3. This question is about the effect of selecting system boundary. We have a piston cylinder assembly with an electrical resistor. So electrical resistor provides heat to the system. We are asked to determine the heat transfer from the resistor to the air in the system. But the system has two cases. System consisting of the air alone, case A, and system containing the air and the piston. So we are going to compare the heat transfer Q for both cases. It'll be clearer to understand the questions by the diagram. So case A, the interior surface of the cylinder and the bottom surface of the piston form the system boundary. Also note that the resistors are not included in the system. This is the system boundary, doesn't include the electrical resistor. Force is applied to the system by the piston. So we take the energy balance on the piston to determine the work. So piston with the force by the mass of the piston times G. Also force by the atmospheric pressure. So these two forces are balanced by the pressure in the system. So we can write the energy balance equations, force balance equations equals So case B, the interior surface of the cylinder. Also exclude the electrical resistor. And this time the system includes a piston. So top surface of the piston forms a system boundary. So force is applied to the system by the atmospheric pressure only, since the piston is within the system. So we are going to compare the result. So let's compare the heat first. Q, in case A, 15.36 BTU. Case B, 15.35 BTU. There's a small difference, but the small difference is due to the round off errors, but they are very close to each other. So there's no difference in heat It's not dependent on the how we select the system boundary. Now compare the work. Case A, work is 4.56 BTU. Case B, work is 4.35 BTU. So when the system includes the piston, work done on the system include the mass of the piston. Case B, when the system includes the piston, work done on the system does not include the mass of the piston. That's why W in case B is smaller. Instead, the change in potential energy of the piston was included in the energy change of the system. So from this question, depending on how the system is selected, the mass of the piston was considered as the work in case A, or potential energy change in the system in case B. Example 2.5. This example we need to apply energy balance in time rate form. A silicon chip measuring 5 mm on a side and 1 mm in thickness is embedded in a ceramic substrate. At steady state indicates there is no change in properties with respect to time. The chip has an electrical power input of 0.225 watt. The top surface of the chip is exposed to an coolant whose temperature is 20 degrees Celsius. The heat transfer coefficient for convection between the chip and the coolant is 150 watt per meter squared per Kelvin. If the heat transfer by conduction between the chip and the substrate is negligible, or we can say the bottom surface of the chip is insulated. Determine the surface temperature of the chip in degrees Celsius. So in these questions, we neglect the heat transfer from the side surface of the chip. We only consider heat transfer from the top surface. Only consider the heat transfer from the top surface and neglect the heat transfer from the side surface. Chip is a closed system at steady state. There is no heat transfer from between the chip and the substrate. Also, the bottom surface is insulated well, so there is no heat transfer from top surface to the bottom surface by conduction. So we only consider the convection between the top surface of the chip and the surrounding fluid. And since the power is given, we are going to use the power rate form of energy balance. So energy balance can be written dE over dt equals Q dot minus W dot. Since it's at steady state, there is no change in properties with respect to time. So there is no energy change. So Q dot minus W dot is 0. And there's a heat convection between the top surface and the surrounding. So Q dot can be written HA, temperature difference between the solid surface and the surrounding fluid temperature. And heat is removed from the system, so heat is going out of the system, so we need to add negative sign here. Plug this Q into energy balance equations. Minus W dot. So we need to solve it for the top surface temperature of the chip, TB. And W dot, work. Work is provided to the system. So work is negative sign. Negative 0.225 watt. Convection heat transfer coefficient is given. And heat transfer area is the top surface of the chip. And fluid temperature is given, converted to Kelvin. So the top surface of the chip is calculated. A system may go through a series of processes. A system is called a cycle if the final state ends at the initial state. So it may experience several states, but the final state returns to the initial state. So the net change in the property values for a cycle is 0. For example, consider a PV diagram. Y-axis P, pressure, x-axis V, volume. So initial state is 1, and it goes through state 2 and 3 and 4. So initial state 1, it moves to state 2, then state 3, then state 4, and we return back to initial state 1. So again, initial state and the final state are the same. It is a thermodynamic cycle. For thermodynamic cycle, there is no net change in energy of the system. So delta E in the cycle is 0. So Q cycle equals W cycle. I will briefly introduce power cycles, refrigeration cycles, and heat pumps cycles. They will be discussed in depth later in the semester. So power cycles, refrigeration cycles, and heat pump cycles are energy conversion cycles. So power cycles is used to provide work during the cycle. And refrigeration cycles and heat pump cycles use work to transfer heat from a low temperature to a high temperature medium. They are essentially the same cycles. Refrigeration cycles and heat pump cycle, they are essentially the same cycle, but they are used for different objectives. Refrigeration cycle is to provide cooling. Heat pump cycle is to provide heating. The performance of power cycle is defined as thermal efficiency. Thermal efficiency is defined as the desired output over required input. So desired output. So power cycle provide work. So desired output is the W cycles, and required input, we need to provide heat. The performance of refrigeration cycles and heat pump cycles are defined as coefficient of performance. Coefficient of performance also expressed as desired output and required input. So coefficient of performance for refrigeration cycle is better. So desired output is Q in. Refrigeration cycle is to provide cooling. So we are interested in the cold body. How much heat is removed from the cold body? So coefficient of performance beta is Q in, desired output Q in, over how much work is required to move the heat from low temperature to high temperature. So required input W cycles. The performance of heat pump. is coefficient of performance denoted by gamma. So desired output here is Q out. We are interested in this area, this space, to provide heat. Move the heat from low temperature to high temperature. So desired output is Q out, and work need to be done to move the heat from low temperature to high temperature. So coefficient of performance Q out over W cycle. So we learn about thermodynamic cycles more in depth later in the semester. So this concludes chapter 2.